Today, we are going to pick up talking about acids and bases, and I want to spend a second reviewing some of the calculation tools that we've been using when you go from pH to POH, and then the negative log of the concentration, and then taking the base 10 and raising it to your pH or your POH to kind of work backwards to get the either the hydronium ion concentration or the hydroxide ion concentration. And this chart, as it's in your notes, but it's also on in your book on page 417. And it just kind of, it's a bit of a flow chart that tells you, if you start with something and you want to get to somewhere else, how do you do those calculations? So with this as a review, I would also want to tell you that, the chart that you guys turned in on Thursday, everybody turned it in with the chart where you filled in all the values. If you didn't notice, I posted a PDF, and it's a packet of pH, POH type problems. And then within that, there's sheets of exercises, practice problems, etc. And then as you scroll down, there are the answers. So I want you to check your answers from the chart that you turned in Thursday. The answers are on there. I think you just scroll down to maybe page 3 or 4, and you'll see all the answers in blue. I want you to check your own work. Make sure you did those correctly. And if you missed one or two, I'm not too worried about it. Feel free to ask, email, or come to office hours. That's a great idea. If you had no clue and you missed them all, definitely come to office hours, because it's so hard to explain this over email. And I am, some of you come all the time, which is wonderful, and I love seeing you, and some of you I rarely see. So if you did not understand that chart, please, please, please come in. Just check your answers, see how you did. But this is a good review for you. It's just, if you can pick any yellow box here that's outlined in purple, but the kind of the tan or the yellow. And if you start with the hydroxide ion concentration, and you want to find the POH, you follow this arrow. And you just take the negative log of whatever this concentration is, and that will give you the POH. Now, if the problem asks you, if you're given a hydroxide ion concentration, or you're given a concentration of a base, and you go to POH, but the question asks you for pH, well, find the POH and then use this equation where pH and POH are combined to equal 14, and then you get the pH. So you can subtract whatever the POH is from 14, and that gives you pH. You can work backwards. If you're given a pH or a POH and you want to find the hydronium ion concentration or the hydroxide ion concentration, you do the inverse operation to the negative log function, which is take the base 10 and raise it to the negative. If you have pH, so you take it to the negative pH and you get the hydronium ion concentration. Or if you're given POH, you take the base 10 and you raise it to the negative POH, and that gives you the hydrogen ion concentration. Then you can also do something else that you may not have focused on too much in your problem solving. That's okay. There are 3 or 4 different ways probably to approach most of these problems. But if you're given the hydroxide ion concentration, and you need, for whatever reason, to find the hydronium ion concentration, you can use this formula, because we know that the hydroxide ion concentration times the hydronium ion concentration is going to equal 1 times 10 to the negative 14. So you can fill either of these values in and then divide to get the other. All right. So if you, as you're doing some more problems, and we'll continue to practice these types of problems, look at that chart on page 417 or just here through the notes. Now, we're going to move on and do a little more in-depth look at acid and base strength. Now, you can look at, if you have an acid-base indicator, you can get an idea just by the color of the indicator in some cases. So with a piece of litmus paper, it's a gradual, bright red to bright blue, depending on how strong or acid the base, or how strong each of those are, but it doesn't give you an actual number. So it would be hard to say which one is stronger when you want to truly compare individual acids and bases. So we have some calculations that we can do with that. Now, a strong acid is defined as something that gives up a proton easily. So think that we're kind of talking about it in terms of that Bronsted-Lowry definition, where they donate a proton or H+ ion. And there are really only 6 common strong acids. All right, so really only 6 that would be classified as something that basically completely gives up its hydrogen ion, and there's not much of an equilibrium backwards. So it's mostly the forward reaction that occurs. These are the 6, what are commonly known as the 6 common acids. So HCl, hydrochloric acid, hydrobromic acid, hydroiodic acid. This is called sulfuric acid. You got the sulfate group here, sulfuric acid. Sorry, my dog just walked in, making a racket. And then you have nitric acid. So these are 6 strong acids. Now notice what they all have. It's very easy to see this hydrogen, and in this case, 2 hydrogens, that would be donated. They ionize completely. So when they go into solution, they completely break apart. And you have H+ and NO3- in the water. Weak acids don't ionize completely, and you get that equilibrium back and forth. Much more of an equilibrium situation than with the strong acids. When we talk about weak bases and strong bases, well, it's just the opposite. A strong base, using the Bronsted-Lowry definition, easily accepts protons, whereas the weak bases don't as strongly accept those protons. And there's not really a good list of those strong bases. I could give you a few, but mostly they are hydroxides. When a compound has a hydroxide attached to an active metal, so like those group 1, group 2 metals, those are the ones when they're attached or combined with a hydroxide ion that are your strong bases. So like sodium hydroxide, lithium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. And then if you go to group 2, you'd see magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Those readily give up their hydroxide ions. But there are plenty of other things that act like bases but aren't as strong, and so they're the weak ones. They don't accept protons as readily as those strong bases do. And then remember, we talked with the Bronsted-Lowry definition, we talked about the idea of conjugate pairs. So the conjugate pair of a strong acid or a strong base is always the weak opposite. So if you have a strong acid as a reactant, its conjugate base is going to be weak. And if you have a strong base as a reactant, its conjugate acid is going to be a weak acid. So acids and bases, remember, think back to chapter 15 in our equilibrium chapter, we had ionization constants, how readily these substances would ionize in water. And then we talked about KSP values. Well, when we strictly talk about acids and bases, it's a similar idea, except we have Kas for the acid ionization constant, and we have Kb for the base ionization constant. And if you remember that Kw value, 1 × 10⁻⁴, is going to be is going to make a steady appearance throughout this chapter, because what you're going to find is that when you take the Ka of a substance and multiply it by that substance's Kb, it's going to be equal to Kw. So let me expand this just a little bit so it's not so jumbled. So stronger acids and bases have higher Kas or Kbs. So like HCl has a very strong Ka, and that means that it completely dissociates in water, and that equilibrium is shifted all the way to the right. So it has a very high Ka above it, with a value way above 1. Likewise, sodium hydroxide has a very high Kb, meaning it really just completely ionizes and readily gives up or accepts a proton. So when these constants are available, and again, there's a table, let me show you this. It's on page 419. So as I'm talking, I would like for you to get your book out as you're listening to this and look at this table. Sorry, let me get it there. Because there's a few things to point out when you look at this table. It's on page 419. It's called table 16-4, relative strengths of some acids and bases. This is not an exhaustive list, but you'll see at the top of the left-hand side, you'll have your acids, and then and it starts out with the strong acids. And then on the right-hand side, you'll have a list of bases, and at the bottom are your strong bases. And then there are guides along this table. So as you're looking at your book right now, which I hope you are, you'll see that on the left-hand side, it's labeled increasing acid strength, and the arrow points up. And then on the right-hand side, it's labeled increasing base strength, and the arrow points down. So on this table, the strongest acids are at the top and the strongest bases are at the bottom. And then if you'll look, it's got the name of the acid, so perchloric acid, which is one of those strong acids we talked about in that list, those 6 strong acids, HClO4. Notice they don't even put a value there for Ka because it's so big. It completely ionizes in water, so it's a huge value. Okay, so they just say large. So that those 6 strong acids we talk about, they don't even give you a value for Ka because it's a complete ionization process. But then, as you start moving down the chart, the acids get weaker and weaker and weaker. Now look at the next closest, what we consider a weak base. It's sulfurous acid in this chart. And look how similar it is to sulfuric acid. You have H2SO4 and then H2SO3. And then the Ka value is 1.3 times 10 to the negative 2. So it's less than 1, meaning it still favors the reactant side, because remember those constants are found by the concentration of the products divided by the concentration of the reactant. But it's not tiny. But then if you go all the way down to the substances that are listed at the bottom, like methane, while it looks like it has hydrogen ions that it might want to donate, that CH4, it doesn't want to, because those are covalently bonded to that carbon atom, and those bonds are really strong. So it's not even measurable, the Ka value. It doesn't act like an acid at all. It's not going to donate its protons readily at all. It's not going to ionize in water because the carbon is bonded to those hydrogens covalently, and those bonds are much stronger than the ionic compounds, the ionic bonds. It also, we'll talk about this later, has to do a little bit with, remember that term electronegativity? We'll talk about that in a little bit. Then let's go over and look at the bases. Okay, notice that the bases here are the same thing, except it starts at the bottom with the strongest bases that are listed. And it just moves on up because it's a comparison. So look at methane and then look over to the right. You have a methide ion. So these are like acid and conjugate base pairs, okay? And it's showing you that if you have a very large Ka, like with perchloric acid back up at the top, the Kb, its conjugate base, is going to be very small. You have a large Ka, a small Kb, okay? Hydroiodic acid, large Ka, small Kb with the I- ion, because that's its conjugate base. All right, so on the left-hand side, you have your acids. On the right-hand side, you have their conjugate bases, and you can compare the Ka versus the Kb from acid to conjugate base. And remember, if you have a strong acid, its conjugate base is going to be weak. If you have a weak acid, its conjugate base is going to be stronger. That's how that works, and that's what this table is trying to show you. Okay. Let me see, how much time do I have left? I didn't want to. Last word as we talk about polarity here. Remember polarity? It was how strongly an atom pulled electrons toward it. Okay, do you remember that conversation? So if you had certain compounds like water, oxygen is electronegative. Do you remember this? And so that's why you had like the Mickey Mouse shape for water, because oxygen pulls those electrons towards itself. So the electrons, even though they're in that same bond, each hydrogen atom is bonded to that oxygen atom. Those electrons that they're sharing are hanging up tight, real close to oxygen. So that makes it a polar molecule. So polarity plays a role in how weak or strong an acid or base is. So the strongest acids have more polar bonds. The strongest bases have these bonding sites that are more negatively charged. All right. So remember, the idea of a base is it wants to readily donate that proton. So the difference in electronegativity between a hydrogen ion or an atom and what it's bonded to will make a big difference. So like HCl, think about that. Hydrogen compared to chlorine, chlorine is much more electronegative. So in that bond, those electrons are going to be pulled towards chlorine, making that hydrogen very easy to donate. Same thing with HI, same thing with HBr. You have bromine, which is very electronegative compared to hydrogen, pulling those electrons towards bromine. And so that hydrogen is very easily able to be donated with, and that's why it makes it such a strong acid, because those hydrogen ions just, they're ready to go, because they're not being held tightly because the electrons are shifted towards the fluorine atom. Okay. And if you look on another table on page 420 in your textbook, you'll have a list of compounds, and they're listed at the top, weaker acids, and it goes on down. And you can see how a difference in electronegativity of that central atom that these hydrogens are bonded to, how it makes a difference. Okay, because if you look on this table on page 420, HF is stronger because that electronegativity for fluorine compared to hydrogen is much greater. So fluorine is going to pull those electrons in, hydrogen is going to pop off, and it's going to donate that proton. And then as compared to methane, it's not as electronegative, that carbon atom, and those bonds are covalent there. So methane does not want to give up. The difference in electronegativity between carbon and hydrogen is not that great as compared to, say, hydrogen and fluorine there at the bottom. Okay, so that also, the differences in electronegativity and whether or not you have a polar molecule make a difference. Okay, and the last thing we'll talk about is that in order to be easily ionizable, the nucleus of a hydrogen atom must be exposed. And again, that means those electrons are shifted away from it. Okay, they're shifted away from the hydrogen in that in that bond between a hydrogen and an atom. So you have hydrogen over here, another atom over here. Those electrons are hanging out toward this other atom that's not hydrogen, because the electronegativity difference pulls those electrons closer. This hydrogen atom says, I'm not as attracted to you as I thought, and it will pop off onto water. Okay, that's what it means. The nucleus of the hydrogen atom must be exposed. Those electrons aren't surrounding it, or the electron isn't surrounding that nucleus. It's being pulled in a tug of war towards that most electronegative atom. And then you have the electrical charge of a molecule also determines the strength of the acid. So the greater the electronegativity difference in that dipole moment that you're creating, the stronger the acid is going to be. All right, I will stop there. No calculations today. So a little bit of a breather, more theory and why acids are strong or weak, or why bases are strong or weak. A few problems to follow up with that. If you're watching this before my office hours on Monday and you didn't understand Thursday's assignment, please come to office hours. Those calculations are not going away, and I want to help you understand them. Think about how we do it in class. We go over problems together. You guys talk to each other. So if you have questions about the assignment, either from the chart after you've checked your work, or those problems, those 10 problems that you were to do on Thursday, please, please, please come to office hours. It's so much better when you guys can talk to each other and ask me questions live. All right. Anyway, I hope you are off to a good start to your week, and we are in the home stretch, and I still We'll say it every day. Miss you guys.